and that was tragic. Okay. Heads up is basically looking forward to the way you budget your study time and attentions with other classes in this class. I'm going to be honest, however much time was spent on this class in preparation for the first unit was kind of abysmal, so let's pick it up for the second one because the difficulty goes up. So think about how much effort you put into the class for the first unit and the output, and then now consider that the second unit exam is definitely a notch up in difficulty, and so make the adjustments that you need to make. Chapter 4 is going to play a humongous role in this, okay? So the exam is happening after the spring break. So that was intentional when we were designing the calendar because we know that this is a really long unit. So that's an extra whole week to kind of go back. Over the spring break, I'm only going to be gone for a few days for medical stuff, but I will otherwise be on campus. So if that's a time you want a ton of extra tutoring and help and catching up, that's the time to take advantage of it because I will be around, okay? So chapter 4 is going to be really, really big. Make sure you don't view each section as isolated and individual. Really, really try to get used to how math will interconnect these things. It's kind of like when you're reading a book and you're reading a story, say like a Jane Austen story. I wouldn't read chapter 1 and 2 and then just pick up the book later and then start reading in chapter 3 and think I started reading a different book, right? You still need to remember the characters. You still need to remember the main motivations of who's involved. The undercurrent plot still matters to what happens in the chapter that you're currently reading. That should not be different in your mind when you study mathematics. This isn't section by section, unit, topic, I do my homework, topic, I do my homework. No, it's we introduced characters, and suddenly it's going to get really hard to follow the plot of this story if we've just decided to forget half of the characters involved in the story, okay? So lots of these things are going to come back up again. Column spaces, null spaces, pivot positions. I mean, characters all the way back at the very, very beginning of this story, all right? So think about your math like that. It'll help probably with the review process because then you're not just thinking of a list of topics, but you're thinking of a list of dependencies. You're thinking of a list of conceptual dependencies. Which sections truly rely on understanding previous ones? Because then understanding certain key sections is going to give you kind of by default the understanding of the other ones if you really get those base concepts in. So when we're talking about dimension, it's a very, very similar thing. This lecture and the next, I would like it to be considered almost the same exact lecture. Because one is a restating in a more, like in the theorem sense, what we talk about here, okay? So let's introduce the goal for the section. Our goal is that this discussion of dimension should lead to insight about into the properties of bases, into properties of bases. So notice we're still talking about bases since we've defined them. They're still very important. They're kind of the driving factor with this entire discussion. Here's a theorem. I'm going to put down two theorems and a definition. So theorem, if a vector space V has a basis, let's call it script B, let's put n vectors in it, so from B1 to Bn, then any set in V, all that means is I've taken a set of objects where those objects are coming from the vector space, containing more than n vectors, must be linearly dependent. Okay, we won't do the proof for that, But think about this intuitively. This is very, very similar back to what it was a while ago in the lecture. But remember when we were talking about if you have more columns in a matrix than you actually have rows, then that kind of just like logically forces there to be the existence of free variables, right? There's no way you can get one-to-one correspondence if you have way more variables than you actually have rows to accommodate them. Ergo, you introduce free variables, and then you introduce all these other problems, right? So one of those problems, consequently, was that you had linear dependence. In other words, there were many ways you could get to zero vector other than just a trivial solution. And so this is really kind of pulling on that same intuition. If I've got n basis vectors, this is supposed to be like the maximally efficient way to span an entire space. If I then take any set that contains more than the quantity of what's required to describe the space, you're just logically forced to be in excess. And then the moment you go into excess, that means you are now introducing and forcing there to be some sort of dependence, okay? And so that's a good intuition. So you don't have to prove that run rigorously, but mentally be able to kind of justify that from what you already know. Here's another one. If a vector space V has a basis of n vectors, okay? So n vectors, that is, it takes n vectors to basically most efficiently span your entire vector space. Then every basis, because remember, bases are not unique. You can have multiple different types of bases for any given vector space. But we can know that every basis of the vector space V must consist of exactly n vectors as well. Exactly n vectors. Okay? So all that's saying is, again, the proof for this is very definitional. If you have a basis and you require n vectors to get that basis, then that's just saying no matter what vector space you choose, all bases have the same number of vectors in them. Which makes sense, right? You wouldn't want imagine you have a bunch of bases, and then one of those bases has one fewer vector than all the others. Then you think, well, hold on a second, how is that supposed to happen? Because this is supposed to be linearly independent by itself and span everything. So that eliminates any possibility of there being alternate sizes. So the moment you find a basis for a vector space, then that's kind of all there is to it. No matter what basis you then look for, if you choose a different perspective, it's required to have the same number of objects. And we can get that. So we don't have to prove that one rigorously here, but mentally sketch why that has to be the case, okay? So let's talk about finite and finite dimensions. This marker is crying for mercy, so I'll give it a break. Definition. There we go. If V is spanned by a finite set, okay, is spanned by a finite set, then V is said to be finite dimensional. Finite dimensional. Nothing profound, nothing crazy, straightforward. And the dimension, and the dimension of the vector space V, which we denote, so denoted dim V. This is really important for the next section, so take note of this definition. This is the number of vectors in a basis for V. pause right here to teach you how to think like a math person. If you've just concluded that every single basis has to have the same number of vectors, just the way that's how the definition of basis works, they all need exactly the same number of vectors, then it makes sense that to set our dimension and to define dimension now of a vector space as that specific quantity, which we definitely know is constant, makes sense, right? We don't want the dimension of our vector space to suddenly be some subjective measure of a perspective, right? So this is going to be a constant per each vector space, unique per each vector space, the dimension. Okay.
So what do you mean by a finite set? Do you mean like the exact amount of set, or do you mean like a small amount of set? What do you mean by finite?
If it's countable, so not infinite. So as long as you don't have like an infinitely many list of vectors, you're finite.
Or you could show what numbers. You could show what numbers. I don't know how to say it.
Well, like if I had a list of V1 through Vp, and as long as P is an actual real, index number that's not just blowing up to infinity, that's finite. Everything we've done in the class so far is finite dimensional. We haven't done anything with it.
Is that hinting that we're going to do stuff that isn't?
Not in this class, but if you go on to topology, those lectures are up on YouTube. You could study more infinite spaces. Okay, so the dimension, and this is just a technicality that we need to introduce, the dimension of the zero vector space, which is basically just the vector space that contains only the zero vector. Technically, the zero vector is one element, okay? But because it's the zero vector, then we're going to definitionally make this the dimension of the zero, okay? So by definition, we're calling this dimension zero, okay? So the space, the zero vector space is defined to be zero. In a similar sense that we just definitionally define 0 factorial to be 1 because we need to have that, but there's not necessarily like a proof for that. It's just definition, okay? And then if V is not spanned, by a finite set, so basically, if it's not possible to span the entire vector space using only a finite number of vectors, then V is said to be, and I'm sure you could extrapolate the terminology here, instead of finite, infinite dimension. Okay, so here's some examples, just so that we can anchor ourselves out of the sum of the theory into just, you already know this stuff, and I'm going to show you that you already know this stuff. The dimension of the vector space Rn is precisely what you intuitively think it is, right? It's just n. Because, I don't know if I've introduced this terminology to you, the upside down Illuminati dots, okay, this is because. Okay. Because you can think of it as indication of, I'm about to give the reason for why I can know what just came before it. The standard basis, that funny looking E, is always just this E1 through En. So no matter what I do, that basis has n vectors, ergo the dimension is going to be n for that vector space. The dimension, if I took the vector space of all real valued quadratics, so P2, okay, well, what's that dimension going to be? Tempting, isn't it? Yes, it's 3. We need to add one. Why, you ask? Well, think about it. What is the basis here?
Oh, x squared, x and c.
We need t to the 0th, which is 1, t and t squared. So the basis elements, we require 3 basis elements to construct quadratics. Ergo, all quadratics require 3 basis elements, and so then the dimension is 3. So in general, the dimension of a n degree polynomials vector space is what? Yeah, just add 1. Because you'll start with 1, t squared, so on and so forth, to t to the n. And so you'll have n elements there, and you're adding on t to the 0. Zero indexing.
This is Scott. This may be a dumb question, but when you think the dim R, the last two are those P's?
Yes, yeah. It's a double struct P.
Okay, that makes sense.
Yeah, handwriting tip. If you want to make fancy double script stuff, so for R's, do a line, make a parallel line to it, and make a capital R next to a line. That's a really good style. For polynomials, make a slightly short line, start on the outside now, go right above it, and loop around. Nice and styled for you. Okay? For a script B, start your pencil at the top of where you want it to be, drop it down, and start curving over to make a loop. Once you get to here, don't connect, and then scoop. Anyway, sometimes that's helpful for handwritten notes. Okay, does this make sense? So dimension is as intuitive as it seems. There's a lot of words for it, but it's straightforward. Let me give some more examples here. Now, before I write this down, what dimension intuitively is a line? Yeah, it's a one-dimensional object, a line. But we can also think of the line as being the span of how many vectors? Right. So if I let some h be the span of a singular vector, then say maybe, it really doesn't matter what we choose, but let's just pick a value so that we can draw a graph, right? So maybe 101, then that means we're spitting out a line. So here's my axis, x1, oh wait, sorry. Oh, that was right, sorry. X1, x2, why am I doing this in R3? Because this vector is in R3. So 1, 0, it's going to be this line that looks like what? This. It'll go along this plane. So if I take all possible linear combinations, that's visually what's happening with that span there. Okay? So it makes sense that since the basis is just V1 itself, this is a basis for H. So, the dimension of my subspace H is so these solid bars when placed around a set indicates how many elements are in the set. So the order, how many elements are in this set? 1. Okay, so this is basic. What this is saying, counting and all this jargon, is simply this. A line is one-dimensional. Yes?
Yeah.
Okay, I'll do one more simple example to extend this to a plane and just to really emphasize this idea that you already know this stuff. We're just giving it a more refined language to discuss in other vector spaces. So now, what about a plane? How many dimensions do you think a plane has? 2, right? Why do we know that? Because, I mean, open your eyeballs kind of a thing, right? So if I have V1, V2, and suppose now that I have V1 is equal to 3, 6, 2, and V2, it needs to be linearly independent, otherwise I don't have a basis. So let's just use something different, like minus 101. Then, when I actually visualize what's going on with the span, I already anticipate this is going to look like a plane, and so all the linear combinations for that first vector coming out like this, and then the other vector kind of pointing up in this direction there, and so then all these linear combinations can be accessed on this plane that gets generated, okay? So this plane, that region in the space, that is what we are referring to by our H. And intuitively, yeah, a plane has 2 dimensions. And so we would say, since the set V1, V2, is it a basis or no?
Yeah.
Yes, it is. It's a basis. Basis for what?
H.
For my subspace H, which is, in this case, the subspace is the plane, like visually. Then we can conclude what? We can conclude that the dimension dim H bush is equal to the size bush of how many vectors are in my basis. The concept that I'm trying to really show by parallel here is that we obtain the dimension of a subspace by counting how many vectors must be in the basis. Okay? Those 2 things go hand in hand. So how many vectors are in here?
2.
So what's the dimension?
2.
That's the connection, okay? So we're saying that a plane is 2-dimensional. I'm sure you can extrapolate this into higher dimensions. Yes, question?
So with the notation that you're doing, so the 2 lines that are usually like absolute, that
Yes.
makes sense.
That's indicating spit out the quantity of vectors in the set.
Okay.
It's an operation, yes.
So is it different than absolute value or?
Yes.
Okay, making sure you just, I didn't understand.
Context will let you know whether it's absolute value or what we would consider the order. We call it the order of a set.
I don't know, I was just seeing if like I remember like when I was a kid doing 3x3 matrices and now knowing like how they actually work as a determinant.
Ah.
You know, I was seeing if the absolute value was actually that, just another.
No. Yeah. Here's how you know. If you ever see the absolute value bars, but you're putting an actual like set in there, that means this isn't about absolute value, this isn't about that. It's just literally count how many objects are in that set, and that's all. Yep. Good clarification for notation. Okay, here's a little bit more involved example that will probably be reminiscent of some of your homework. Find the dimension of this subspace H if we're given this. Now, we're defining a subspace H by sets of vectors of the form A minus 3B plus 6C, 5A plus 4D, B minus 2C minus D, and lastly 5D. So vectors that have this form for all A, B, C, and D as scalars, okay? So any combination of these scalars in this specific format, that's the type of vectors that make up this subspace H, okay? So how do we find the dimension? Because this is not intuitive anymore, okay? I can't just look at them and be like, oh, well, obviously it's a plane, okay? So I can't do that. What do you do? What do you do when you get one of these general form things? Well, don't forget your skill that you learned before about decomposing in terms of the common terms, right? So I can split up all the A's, B's, C's, and D's. So I change my perspective of it. When I look at this representation of A minus 3B plus 6C, 5A plus 4D, B minus 2C minus D, and 5D, well, let's make this easy. Let's clump all of the A terms together, all the B terms, etc. So in the top, I have A, I have 5A. Do I have any A's here? Okay, yeah, nothing. What about on the bottom? Okay. And then let's do all the B's. So I have minus 3 of them, so minus 3B, 0, 1, 0. Okay, you guys start shouting these out. What about the next vector here? 6C,
0,
0,
2, 0.
minus 2C, and 0. And the last one?
0, 4,
4D, negative D, 5D. Okay, I hear people shouting out the coefficients, which is great, assuming you've mentally factored out your letter beforehand. If you forget to do that, then that might lead to some problems. So when you're factoring out your actual components now, it's 1, 5, 0, 0. And this is what I mean by decomposing a vector solution. Oopsie. Also, I caught myself making a mistake earlier. So in this vector, that should be a b, not just a 1. And then this is c times 6, 0, minus 2, 0, d times 0, 4, minus 1, 5. Okay, so now let's start looking at these as vectors. This is v1, this is v2, this is v3, and this is my v4. When I start looking at these as vectors, why am I doing that? Well, because definitionally, what do I have? Linear combination. I've taken scalar weights to a bunch of vectors. We know how to deal with linear combinations, okay? So all the behavior comes into play. Now, this is suspicious because I know that I could take v3, and really v3 is just this vector if I were to multiply it by minus 2, right? Which introduces a problem, right? Because what does that say about this overall set of vectors? Yeah, we're dependent right now. How do we trim out the problem to make it independent? We just eliminate the one that actually is depending on something. So we say, sayonara, he's gone. Okay, so when I make my basis, I now have vectors v1, v2. That was unnecessary. That was a problem. It was introducing dependence, so I'm not going to count it. And then I go to v4. And you could show more rigorously that those 3 vectors that are left are actually truly independent from each other. Okay, so this is my basis. Fantastic. It's a basis for what? For h. And if it's a basis for h, and we're interested in the dimension of h, do you remember the definition of the dimension of h? The quantity of vectors in my basis. So the quantity of vectors in my basis, which if you count that up, is just 3. Okay, so whenever you get a problem type that says find dimension of, and then they define some random subspace, if they give it to you like in a way that you can just decompose this vector form into a linear combination, now you're looking in terms of dependence and independence, strip it down to just the basis, which is only independent vectors, and then count how many are in that basis. And there you go, it's a procedure. Okay, so these are some examples, some classic examples that you'll need to know. Questions, comments, concerns about any of this? Okay, because really now I want to spend the rest of the time on what I consider the most important part of this lecture, which is going to set us up for Wednesday's discussion. Okay, so this is all just to make sure we know what the definition is, how to interact with the definition in basic examples. But now, to tie back to other content, the theory. Because this is where the theory is going to start producing really nasty shortcuts that are going to make some of this previous work happen a lot more efficiently, okay? But it takes some time to build, so we will give it the time it needs to build. Theorem. Let's let H be a subspace. Be a subspace of a specifically finite dimensional vector space. V. And then any linearly independent set, any linearly independent, such a long word, set in H can be expanded if necessary, because sometimes you don't need to, if necessary, to a basis for H. Also, Think about it. If V is finite dimensional, then a subspace is also finite dimensional. So H is finite dimensional. And here's the main inequality that's important. The dimension of your subspace will always be less than or equal to the dimension of the overall vector space from which it comes. Again, this is a pretty intuitive idea. Bigger object being greater than or equal to a smaller object. This is real profound stuff. You're paying tuition money for this, okay? Now, note that subspaces, like the trivial subspace of V is V itself, because V is technically, it's a subset of V. So that's why it's an inclusive. But also it could be inclusive because you could find that you require the way that you define H, that it requires still the same number of basis vectors. So at any rate, that's all this is saying. It's big thing happens to have at least more dimensions than the thing that's supposed to be coming from it, right? Smaller thing, smaller than a bigger thing. Okay. Like, imagine you take a ping pong ball, and then you use your fancy equipment over there in the NEC to like slice out a sliver section of it, okay? So you're essentially taking a subspace of your sphere ping pong ball, and it's a circle, right? Okay, well, that's gonna have fewer dimensions than the overall space that you know, okay? So, nothing crazy there. This only gets really crazy until you get to topology when common sense now has to be proven, and then that's for grad school. Okay. Next theorem. Oh yeah, this is the big dog for the second. Okay, yeah. Okay, we'll talk about this quite a bit. Let V be a p-dimensional vector space, and we'll just clarify, for technicality's sake, that we're requiring P to be greater than or equal to 1. So no zeroth dimension or negative dimension stuff. Any linearly independent set. Linearly independent set. I'll rewrite that word. Of exactly P elements, in V is automatically a basis. Automatically a basis for the vector space V. And even further, any set of exactly P elements that spans V is automatically a basis. A basis for V. Okay. So, again, this, you don't need to do a whole rigorous proof of it, but again, know how to mentally map why this has to be true. This result should feel obvious as a, result of what we know about these definitions. I have p-dimensional vector space, okay? For something to have dimension p, what does that tell me about how many vectors are in any given basis? Yeah, exactly, precisely p. I mean, that's the whole point of these examples, is to show that if your basis has so many vectors in it, ergo the dimension then just is count up the quantity of how many vectors there are. So if we're given from the start that the dimension is p, how many basis vectors are we always going to have? P. Is that something that's allowed to change? No. And we know that from the first two theorems in this lecture. Okay? So this should be pretty straightforward. Is that if you have a linearly independent set of p vectors, G. So I have exactly the number of vectors I need to make up the dimension. They're all linearly independent. It satisfies the definition, so it's just a restatement. The bottom one is a restatement, but coming from the other angle of what it means to be a basis. This time, span, okay? So you have exactly p things for the dimension, and then it's spanning all of v, okay? Well, the only way that's possible then is if it's a basis, ergo, it's a basis. So don't think of these theorems as like completely new material. Most of the time, a theorem in this book is just a succinct mathematical summary of all of the stuff that you've been learning about from the definitions, okay? Couching all the abstractions and couching all the patterns in singular statements that you can refer to for reference. So I'll leave these two up and talk about some of the ramifications of why we care about these theorems. Because there's going to be some shortcuts involved for null spaces and column spaces. And then when we start talking about rank on Wednesday, it'll all be connected together. Okay. So I'm intentionally leaving this up for reference. So if you need to, in your notes. Okay. So first kind of like important observation here. So if I take ax is equal to 0, we call this equation the homogeneous equation. This means a review for terminology. If this has n free variables, that can only happen if the dimension of your null space for a matrix A is n. We'll talk more about this in a second, but for now, let me get the other one up too. Other big takeaway here. If I have a matrix A, and I know that it has n pivot columns, that could only happen if the dimension of my column space is n. Okay, let me see how much time I have. Perfect. Okay, so what I'm going to do is I'm going to leave this up here for a second. I'm going to stew on and do an example, because the example is going to show you in a practical sense why we care about these kinds of generalizations. Because right now, unless you have a really high abstraction module in your brain, that probably doesn't mean too much right now in terms of its usefulness, okay? So let's look at an actual situation. So find the dimension of the null space and also the dimensions of the column space given the following matrix. So let's work with A is equal to minus 3, 1, 2, 6, minus 2, minus 4, minus 1, 2, 5, 1, 3, 8, minus 7, minus 1, minus 4. Because now that's starting to look kind of more like a homework problem, okay? So immediately, part of what I believe is helpful as a math student is to just hear what somebody is thinking about when they first see. My first initial impression when I saw this problem was, gee, that's a ton of columns, considering we only have 3 rows. So there's automatically, I'm anticipating there has to be free variables, okay? And if I'm anticipating the existence of free variables, that's going to mean I have linearly dependent columns. So those free variables are going to allow me to have a bunch of non-trivial solutions for the homogeneous equation. Okay, really think about that for a second. Have I even started attempting to solve this problem with my hand?
No.
No. What have I done? I made a baseline observation about what was given to me, and because I'm familiar with definitions, all of those conclusions that I can make are just dominoes falling and hitting each other as I make observations. Learn to make observations about problems, because that's going to be the fastest way you unstuck yourself from problems you're stuck on, okay? So all of that from just knowing, well, gee, that's a ton of columns, and there are not enough rows, okay? So I'm already anticipating the column space, or at least the null space, having an interesting number of dimensions, right? Because I'm guaranteed to have some sort of a basis for that. And then column space will be interesting too, because if I have more columns than I have rows, I'm still going to have some pivot columns, okay? So let's take a look. What I'm not going, practically speaking, what you'll do with this procedure is you'll still augment with your homogeneous equation, and you'll row reduce it. So I'll take the augmented equation of A with 0 vector, right? So I do my homogeneous equation, and that's going to be minus 3, 1, 2, 6, minus 2, minus 4, minus 1, 2, 5, 1, 3, 8, minus 7, minus 1, minus 4, blah, 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 0, 0, 0. So this is now a homogeneous equation. It's the perspective I'm taking. What I'm not going to do is waste your time with a bunch of arithmetic that I know you already can do. So what this does row reduce to, I'm not going to go, you don't need to go all the way to reduced echelon form. Just an echelon form is going to be fine here. And we'll see why very quickly. So we have 1, 0, 0, minus 2, 0, 0, 2, 1, 0, 3, 2, 0, minus 1, minus 2, 0, and then of course 0, 0, 0 on the other side. Okay. My issue here is not teaching you how to do row reduction anymore, okay? So that's why I'm just kind of shortcutting here so we can talk about what you do once you've done the row reduction. We'll make two observations here. We're going to count the free variables.
Three.
And we're going to count the pivot columns. Okay. So, do you see why we don't need to go to row reduced to get these two pieces of information? You can always get this from just an echelon form. So, my free variables, that's obviously good to go. He's representing that x1. But then I have this x2, and the way you can tell if it's free is if you look immediately under it, and it should be a pivot, and there's just a bunch of zeros. Okay, well, he's just doing whatever he wants. So we're going to have x2. That's a free variable. Okay, here's our next pivot, right? So this is x3. Is this a basic one, or is this one free? Yeah, this is basic. It's doing its job. It's in the pivot spot. Okay, what about this x4, next one? Free. Okay, what about the next one?
Free.
And I should clarify that when I'm pointing, I'm not pointing to the specific number, but rather the position of whether it's x1 through x5 in this case. So, how many free variables do I have? Okay, so I've got 3 of these guys. What about the pivot columns? Well, we actually kind of identified them on the way, right? Here's a pivot right here. So this entire column is a pivot column, and that was the other pivot. So how many columns contain pivots? Okay, and I know that corresponding back to the pivot columns, this is itself not the pivot column for the matrix A. This is a really important distinction I want to make in a lecture with everybody here in person. We row reduce to identify the location of a pivot column, but the reduced form is not in itself the actual pivot column for the original matrix. So I'm like glad that I did this because now I know that it's respectively the first column position and the third column position, but I don't want to take those and conflate those with the actual pivot columns, okay? So we row reduce to expose it, to uncover it, but that is not in itself the pivot column. What do? We take their respective positions and locate them in the original matrix all the way to the beginning. So here we know that there's a pivot in that first column. So that tells me, if I'm looking at my original column, my original matrix, that first column position is going to be a pivot column. So I'll take these entries in here. So I got minus 3, 1, 2. Does that distinction make sense?
Mm-hmm.
Yeah.
Because that's really important. So in order for this shortcut to really feel like a shortcut, we need to know that difference. Okay? So don't be accidentally doing all this hard work just to mistake what your column vector is. Okay. What's the other pivot column for the matrix A?
Minus 1, 2, 5.
Very good. Why do we know it's minus 1, 2, 5?
Because it's the third column.
How did you know to pick the third one? I mean, that seems like a lottery guess.
That's our pivot column in our reduced.
Ah, because when I reduced it in echelon form, that told me where to look in the original. Okay. Does that make sense? That's a reproducible, logical step that you could do in your own homework, yes?
Yeah.
Okay.
Now, you look for the pivot columns, but you don't push it further to the specific pivot positions. They have 1 and 2 there.
No, just think about it. Does the position affect the entire column? I mean, so I just need to identify which column that position is occurring in,
Okay.
because I'll end up taking the entire column anyway.
Okay.
Yeah. Okay, that's really, honestly, when I was making the notes and things that I really wanted to make sure we understood, this is the big one, okay? So if that makes sense, how to identify the free variables and your pivot columns, so in this case we have 2 of them, then that's huge. Because if you can just make those 2 basic observations for any matrix, you will always have the dimensions of your column space and the null space. Here's how you connect them. Let's return. X equals 0 has n free variables. That's only true if your dimension of your null space is what? Okay. Is this not the homogeneous equation? Did we not find exactly how many free variables we have? Okay, so that can only be true, and that tells us what? About the dimension. The dimension of the null space of the original matrix is what? 3. So we took all this work to identify pivot columns so that we know how many we have. What does that force us to conclude about our dimensions?
Dimensions called A equals 2.
Yeah, that means our column space will have the dimension of 2. What does this example show? This example shows that the only skill you need to have to solve new problem types for calculating dimensions of null spaces and column spaces is quite literally just row reduction. That's it. That is unironically the only thing that you still have to be able to do. Okay? If you can row reduce, you can do all sorts of crazy stuff. You can find inverses of matrices, you can calculate determinant stuff, you can calculate dimensions of null spaces and column spaces, you can do all of this. You just need to know how we're able to know. Okay? So, do these 2 statements above the dotted line make sense now in context? Okay. Does the example itself make sense too in context? Is there any doubt in the mind of for sure knowing that that's precisely going to always be 3, that this is not how we get the columns? Yes, we feel good? Okay, because if we understand it at that level, that means we go 1 layer deeper on the null space here. Okay? Woo. Now I'm going to go off notes. No notes for this.
He's going off.
So,
He's free balling.
lock in for a second, all right? So think about what the null space really describes. Okay, so recall, what is a null space?
The set of vectors times your A matrix that equals 0.
Yeah, this is just curious. It's a collection of what gets sent to 0. In other words, it's the solutions to this. So this is going to be our solution set to, so this is going to be solutions. I shouldn't use the preposition to, I should use of the homogeneous equation. Okay, so fantastic. Let's take a look. We actually got it to here. And so if I write out the equations now, I have x1 minus 2x2 plus 2x3 plus 3x4 minus x5 is 0. Then I have x3 plus 2x4 minus 2x5 equals 0. And then I have just a ton of free variables, right? So I have x2, x4, and x5 free. So think about this. All combinations of this solution is going to be good. So I can represent my basic variables in terms of my the free variables to write the basic variables. So x1 is really just, we would have to row reduce echelon form it. So, oopsies. Remember when you were able to write an x vector, x1, x2, x3, x4, x5? Yes?
Yeah.
And when we do this, we're actually placing it. So the ones that are dependent on the free variables, we would need to do, put it in terms of free variables, and the actual free variables would just be themselves.
Yeah.
Now, if we're interested in solutions of 0, to have 3 degrees of freedom means that we have ultimately, we will have 3 degrees of freedom for linear combinations. So if I have a span of my vectors corresponding to x2, x4, and x5. So this is going to be just v1, v2, and v3. These have to be linearly independent if they are factored out from my free variables. So the quantity of free variables is telling me precisely how many vectors are going to be spanning, and if they're linearly independent and they also span, that's by definition basis. So then the size of my basis is going to be 3. And what does the size of what does the size of this basis correspond with?
The number of dimensionals of no.
Right, because dimension is definitionally the quantity of vectors in the basis. Okay? So this is dimension of the null space is equal to 3. You could do the same thing with the, you could do the same exact thing with the column space. Do we remember what the column space really is by definition?
The span of your vector or your matrix.
Just the set of all the columns.
We just want linear combinations of the column vectors. So I have linear combinations of A1 through A5. Okay, well think about it. We figured out the only 2 columns that are actually independent of each other. Because if these are the only pivots, that means every single other column is just dependent extra, okay? So, really, I could span everything with just these 2 independent columns. So I have a linearly independent set of my pivot columns. And since they're linearly independent, their span is the same thing as the column space. So if the span of a linearly independent set is equal to my subspace, this is a basis. It's a basis for the column space. And if this is a basis, and dimension is just how many vectors are in my basis, and then I can go straight to knowing, okay, well then the dimension of the column space is the quantity of how many vectors are required, the quantity of vectors in here that are independent from each other, and that's 2. So when we're circumventing, when we're going from here and cutting to this conclusion, and here and cutting to that conclusion, we're really able to we could find those conclusions by the definitions of each of these things. So it's all related to each other. So if you understand this, it's going to help a lot for Wednesday. Because all we do Wednesday is we introduce one more character, and his name's rank. And we'll just relabel this concept of the dimension of the column space. We'll call that entire quantity the rank. Okay?
That's correct.
So it stacks pretty fast on top of each other. All right, that's time. I will see you Wednesday.
Leave the room. See you on Wednesday.